Hello everyone, my name is Nikman. In this video lecture, we will discuss about the topic rectifier, filter and power supply for mechanical third semester. The subject name is Fundamental of Electronics. So at first, we have to know what is rectifier. A rectifier is an electrical device that converts an AC current, that means alternating current, into a direct current, that is DC current, by using one or more PN junction diodes. So as in the diagram, you can see an alternating current is changed to a direct current by using a rectifier. So next comes, what is the need of rectifier? By rectification, an alternating current or voltage is converted into a direct current or voltage. Next comes, what are the types of rectifiers? Rectifiers are mainly of two types, that is half-wave rectifier and another one is full-wave rectifier. The full-wave rectifier is further divided into two types. One is center tap full-wave rectifier and another one is full-wave bridge rectifier. Next comes the half-wave rectifier. A half-wave rectifier is defined as a type of rectifier that only allows one half cycle of an AC voltage waveform to pass, and it blocks the other cycle. So we can see the circuit diagram of a half-wave rectifier. Here we are using only one diode. In the diagram you can see the AC input is coming through a transformer. It is going to the diode. The AC input waveform and the resultant output waveform is seen in the diagram. Now how a half-wave rectifier works. At first, during the positive half cycle, the diode is under forward bias condition and it conducts. So a voltage is developed across the load which is same as the input AC signal of the positive half cycle, and in the negative half cycle the diode becomes reverse bias. So the diode does not conduct and there is no current flow through the diode. So only the AC input voltage appears across the load, and it is the net result which is possible during the positive half cycle. So we receive the output only one half of the AC wave here in the positive half cycle only. So we can see the input output waveform here. We have seen that the rectified output only in the positive half cycle. Next is full wave rectifier. There is a full wave rectifier with center tapped transformer. Like the half wave circuit, a full wave rectifier circuit produces an output voltage or current which is purely DC or has some specified DC component. Basically, full wave rectifiers have some fundamental advantages over their half-wave rectifier counterparts. Here the average DC output voltage is higher than that of half-wave. In a full-wave rectifier circuit, two diodes are used, one for each half of the cycle. That means diode 1 for positive half of the cycle and diode 2 for negative half of the cycle. Here we can see the circuit diagram. Two diodes are there, D1 and D2, and there is a center tap transformer, and we can see some points, that is A, B and C. We will discuss the points in the working principle part. So let us see how a full wave rectifier circuit works. Now this circuit consists of two power diodes connected to a single load resistance RL, with each diode taking it in turn to supply current to the load. So at first, when the point A of the transformer is positive with respect to point C, then diode D1 conducts in the forward direction and as indicated by the arrows. So the diode D1 is in forward bias condition in positive half cycle. So it conducts. In that condition, diode D2 becomes reverse bias. So diode D2 does not conduct in positive half cycle. When point B is positive, that is for the negative half cycle with respect to point C, then diode D2 becomes forward bias and it conducts, and diode D1 becomes reverse bias and it does not conduct. So as the output voltage across resistor R is the phasor sum of the two waveforms combined, this type of full-wave rectifier circuit is also known as a biphase circuit. Here we can see the input-output diagram. The input is given, then output during the positive half cycle for input is given, then the output during negative half cycle of input is given, and we have combined the total output to get the full-wave rectifier output. Then comes bridge rectifier. Here in this circuit diagram, you can see the circuit diagram of bridge rectifier. In bridge rectifier, there is a 4 diode: D1, D2, D3, and D4. The circuit diagram is given in the figure. Now, how a bridge rectifier works. When input AC signal is applied across the bridge rectifier during the positive half cycle, then diode D1 and D3 becomes forward bias and allows electric current, while D2 and D4 are reverse bias and blocks the electric current. On the other hand, during the negative half cycle, diode D2 and D4 becomes forward bias, so they conducts, and diode D1 and D3 becomes reverse bias, so they does not conduct. So during the positive half cycle, the terminal A becomes positive with respect to, while the terminal B becomes negative. So diode D3 and D1 becomes forward bias and D2, D4 becomes reverse bias. And the current flow direction during the positive half cycle is shown in the figure. And during the negative half cycle, the terminal P becomes positive while the terminal A becomes negative. This causes diodes D2 and D4 becomes forward bias and they conducts, and diode D1 and D3 becomes reverse bias, so they does not conduct. The current flow direction during negative half cycle is shown in the figure. And here we also can see the input-output voltages of bridge rectifier. First one is AC input, then D1, D3 current, and then D2, D4 current, and then the total output current. One for positive half cycle, another for negative half cycle. D1 and D3 conducts for positive half cycle, D2 and D4 for negative half cycle. Next comes rectifier performance characteristics. There are some performance characteristics of a rectifier. They are DC voltage on load, that is VDC, that is equals to 1 by T, 0 to T integral VL into ddt. Form factor is given by VL divided by VDC. RMS voltage is VL equals to root over 1 by T, 0 integral 0 to T VL squared ddt. And ripple factor equals to root over form factor squared minus 1. Then comes the efficiency factor of rectifier. It is also called 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 efficiency factor of rectifi efficiency rectification factor, that is denoted as eta, that is equals to PDC by PL plus PT. PDC is given by VDC into IDC, PL is VL into IL, and PT equals to RT into IL square. The relationship between eta and form factor is also given, eta equals to 1 by form factor whole square. Then comes transformer utilization factor, that is PDC divided by VA rating of the transformer. Then comes ripple factor. Ripple frequency. Ripple frequency is the frequency of the residual AC voltage after it has been rectified to DC in a power supply. It rides on the top of the DC voltage. Then comes peak inverse voltage. For rectifier applications, peak inverse voltage, that is PIV or peak reverse voltage or PRV, is the maximum value of reverse voltage which occurs at the peak of the input cycle when the diode is in reverse bias condition. The portion of the sinusoidal waveform which repeats or duplicates itself is known as the cycle. Next comes the comparison of three types of rectifiers. The first one is half wave, then full wave bridge. The number of diodes for half wave is 1, for full wave is with center tap is 2, and full wave with rectifier is 4. Peak inverse voltage for half wave is Vm, for center tap full wave is 2 Vm, for bridge type full wave is also 2 Vm. Maximum efficiency for half wave rectifier is 40.6%, for full wave center tap rectifier is 81.2%, for bridge rectifier is also 81.2%. Ripple factor is for half wave rectifier is 1.21, for full wave center tap rectifier is 0.482, for full wave bridge rectifier is 0.482. Next comes the applications of rectifiers. The rectifier is used for power appliances, used with transformers, used in AM radios, used for modulation, etc. Next comes filter. What is a filter? A filter is a circuit that is capable of passing or amplifying certain frequencies while attenuating other frequencies. So what is the need of a filter? A filter can extract important frequencies from signals that also contain undesirable or irrelevant frequencies. Also, filters are used on power supplies output to reduce ripple. There are different types of filters like capacitor filter, inductor filter, shunt filter, series filter, L-type filter, Pi-type filter. L-type and Pi-type, you can get LC filter also. LC filter is divided into L-type LC filter and Pi-type LC filter. So at first we will see what is capacitor filter. Capacitor filter is the reactance of the capacitance. C of the output voltage is much smaller than load resistance. Advantage is it has no inherent resistance and not bulky. Disadvantage is voltage fluctuation across load resistance is there. Diagram is shown in the right hand side. Then comes inductor filter. You can see the inductance and resistance is connected in series. There is inductor filter. Here the reactance of the inductance L at the frequency of the input voltage is much higher than load resistance. So the AC components of the rectifier output voltage appear mainly across the inductor. The DC components passes through the inductor without much loss provided. Advantages: it decreases fluctuation of the voltage across the load resistance, which was a disadvantage of capacitor filter. So we have recovered that disadvantage by using inductor filter. But the disadvantage of inductor filter is it is bulky and it has inherent resistance. Then comes L-type LC filter. The diagram is shown in the right hand side. Filtering actions of the capacitor and inductor filter are combined here. The series inductor L reduces the ripple voltage and the shunt capacitor bypass them, so a smooth voltage appears across the load resistance RL. Pi-type LC filter. The diagram of Pi-type LC filter is shown in the right hand side. It consists of a capacitor filter and a L-type LC filter. The ripple at the output of a capacitor filter is diminishes as the load resistance is increased. So effective filtering is obtained here for load current less than 50 milliamp. The advantages of LT filter is it requires a low value of C than a capacitor filter for a given amount of ripple. Next comes the rectifiers with filter circuits. We have in the left hand side the diagram is given that half-wave rectifier with capacitor filter. The half-wave rectifier circuit is given and we have introduced a capacitor filter to get a better output. Then in the right hand side we can see the diagram of full-wave rectifier with capacitor filter. To get a better output, we have introduced a capacitor filter in the full-wave rectifier circuit. Here we can see the bridge rectifier with the capacitor filter, bridge rectifier with the LC filter. We have just introduced the filters in the rectifier circuits, what we have taught in the previous slides, to get a better output. Next comes Zener diode as a simple voltage regulator. We can use a Zener diode as a simple voltage regulator. The circuit diagram is shown on the right hand side. Here the Zener diode is connected across the load RL. You can see in the diagram. Now, if you want the voltage across the load to be regulated and not cross the value of Vz, depending on our requirement, we choose the suitable Zener diode with the Zener breakdown voltage near to the voltage we require across the load. So we connect the Zener diode in reverse bias condition. When the voltage across diode exceeds the Zener breakdown voltage, a significant amount of current starts flowing through the diode. As the load is in parallel to the diode, the voltage drop across the load is also equal to the Zener breakdown voltage. So the Zener diode provides a path for the current to flow, and hence the load gets protected from excessive currents. Thus the Zener diode serves two purposes here. The Zener diode as a voltage regulator as well as it protects the load from excessive current. Now, when the minimum input voltage and the maximum load current is happening, then the Zener diode current should always be minimum. So as the input voltage and the required output voltage is known, so it is easier to choose a Zener diode with a voltage approximately equal to the load voltage, that is Vz equals to VL. So the value of the series resistor, that is Rs, equals to VL minus Vz into IL. So the current through the diode increases when the voltage across the diode tends to increase, which results in the voltage drop across the resistor. Similarly, the current through the diode decreases when the voltage across the diode tends to decrease. Then the voltage drop across the resistor is very less and the output voltage results normally. Next comes IC voltage regulators. The voltage regulator is one of the most widely used electronic circuitry in device. It is an integrated circuit whose basic purpose is to regulate the unregulated input voltage and provide with a constant regulated output voltage. You can see the block diagram of an IC voltage regulator. There are different types of IC voltage regulator. We will see the LM78 series. LM78 series, we can see the diagram of the 7805 series. The input, output and ground pin. So LM78 series is basically a fixed positive voltage regulator. Like 7808 produces an output of plus 8 volt. 7815 will produce output of plus 15 volt. 7805 will produce an output of plus 5 volt. Next comes LM79 series. It is a group of fixed negative voltage regulator. that means it will, suppose 7905 will produce -5, 7910 will produce -10. Next is dual tracking voltage regulator. It is used when split supply voltages are needed. That means plus 18 to 30 volt inputs and minus 18 to minus 30 volt inputs. We will get the output of plus 15 and minus 15 for minus 18 to minus 30 volt input. We will get the output of minus 15 volt. So it is the dual tracking voltage regulator. You can see the diagram on the right hand side. Then comes what is the line regulation and load regulation. Line regulation is the ability of a power supply to maintain the output voltage given changes in the input line voltage. And load regulation is the ability of the power supply output to remain constant given changes in the load. Then comes SMPS. SMPS is switched mode power supply. It is an electronic power supply that incorporates a switching regulator to convert electrical power efficiency. Here the voltage regulation is achieved by varying the ratio of on-off time. The advantage of SMPS is it has higher power conversion efficiency, smaller and lighter than a linear supply. The applications of SMPS is to transfer power from a source like main power to a load like personal computing. The block diagram of SMPS is given in the figure. The high voltage AC input first comes to the rectifier and filter, then the output goes to high frequency switching device, then it goes to converted to transformers for step down. The step down transformer converts it to a low voltage constant current, then again it goes to a rectifier and filter circuit. From that it goes to a constant DC output voltage and it comes to output sensor and reference section. Then it goes to a feedback and error amplifier. Then PWM, that is pulse width modulation, pulse oscillator is used, and in the feedback path and error correction path it goes to the high frequency switching device.